Hello dear students. Today we are going to discuss about the production of X radiations. In the previous video you might have seen about the discovery of X radiations, where you might have undergone a statement that X radiations are electromagnetic radiations of very short wavelengths. Now we are going to discuss about the production of X radiations. X radiations are produced by X-ray tubes. X-ray tubes are basically essentially discharge tubes. In a discharge tube, there will be a low pressure maintained, and it contains two electrodes. One is cathode and another one is anode. In this discharge tube, this is a specially designed discharge tube to produce X radiations. A filament F is there, which is provided along with a grid. This acts as the cathode. The filament is connected to a low tension battery. The low tension battery supplies voltage across the filament so that the filament gets heated up. It is heated to incandescence. Incandescence in the sense, any body which is taken to high temperature will emit light. That we used to call incandescence. Sun is an incandescent source. In the same way, the filament is said to be an incandescent source. It is taken to incandescence. It emits electrons due to thermionic emission. So the emitted electrons are just emerging out from the filament, and these electrons are made to move with high speeds with the help of a high voltage applied between the filament and the anode. These electrons are emitted from the filament. These electrons must be focused towards a particular target, and these electrons must be made to move with high speeds. That is very important. The basic definition is there. X radiations, how X radiations are produced? X radiations are produced when the target is suddenly struck by fast moving electrons. When the fast moving electrons bombard a target material of higher atomic weight, X radiations are produced. See this condition? What is the requirement? A target material of higher atomic weight is required. Then the electron must move with high velocities, and it must bombard the electron. See this one? It has to collide. It has with the high velocity. Then X radiations will be produced. That's the main idea. So the electrons emitted must be accelerated with high speeds. So you are applying high voltage across the filament and the anode so that the electrons will be moving with high speeds. The high voltage is provided by high tension battery. Filament is heated by low tension battery. Acceleration of electrons is done with the help of high tension battery. This supplies high voltages. With this high voltage, the electron will be accelerated towards the target. When it hits the target, X radiations will be produced. What is the target here? Target is basically tungsten or molybdenum. Target is basically tungsten or molybdenum, which is embedded on a copper anode. What is this one? Copper. Copper anode is there, over which the target tungsten is embedded. Target tungsten is embedded. So the electron, when hits the target, X radiations will be produced. Right at the same time, the electron, when colliding with the target, will lose all its kinetic energy. Enormous amount of heat energy will be produced. This heat energy must be removed from the discharge tube, so a coolant system must be maintained. A water cooling system must be employed. And the target material should possess a high melting point in order to withstand the heat at the time of bombardment of electron over the target. When electron strikes the target, it loses its kinetic energy. The lost energy is given out in the form of X radiations, and also it is used up in heating the target. When target gets heated up, if the heat goes on multiplying, then what will happen? The discharge tube cannot withstand that amount of heat, the rise in temperature. So the heat generated must be removed from the discharge tube, and that is done with the help of a water cooling system. Right at the same time, copper is a very good conductor of heat. See, large amount of heat will be generated. So the target must possess high melting point so that it can withstand the amount of heat produced. Right at the same time, it is attached along with copper. Copper is a very good conductor of heat, so it will be transferring heat. So when a water cooling system is allowed to pass through, the heat will be carried away from the discharge tube so that you can continuously produce X radiations. This is how the production of X radiations are taking place. Now we shall discuss about X-ray spectra. As I told you earlier, X radiations are produced when high-speed electrons bombard the target with high energies, with high kinetic energies. So when fast-moving electrons strike the target of higher atomic weight with a large amount of energy, the energy possessed by the kinetic energy possessed by the electron will be lost and it will be given out in the form of X radiations. Also, large amount of heat will be generated. Here we are going to draw a graph by taking radiation intensity along y-axis and wavelength along x-axis. Wavelength along x-axis. Two graphs are drawn. One is the radiation intensity, which is taken along y-axis, and wavelength along the x-axis. One is drawn for different accelerating voltages. As we saw in the production of X radiations, we saw a high tension battery is employed to supply high voltage across the electrodes between the filament and the anode. That voltage can be changed. You can increase the value of voltage even to 1 lakh volt. That's why in the X-ray production unit, a high voltage unit will be kept separately. It will be provided separately. So you can vary the value of voltage across the filament and the anode. So we are going to obtain the graphs for different wavelengths and the corresponding radiation intensities for different accelerating voltages. The graph obtained will be of this form. So this is for 20 kilovolt, this is for 30 kilovolt, this is for 40 kilovolt, and this is for 50 kilovolt. Actually, you can see these are all the different accelerating voltages. The intensity of the peaks increases with increase in value of accelerating potentials, and the value of wavelengths are marked along the x-axis. This is one graph. This is a spectra which explains about a continuous X-ray spectra. This is the spectra for tungsten target. Spectra for tungsten target. Also, we can draw a similar graph. This radiant intensity or radiation intensity versus wavelength for tungsten and molybdenum. For tungsten and molybdenum. For tungsten molybdenum, this is the curve which we already obtained. This is for 35 kilovolt. For same accelerating potential, we got two different curves. One is for tungsten. Another one is for molybdenum. You can see the minimum wavelength for both the intensity curves is same. For tungsten as well as for both the targets, the minimum wavelength is same. We just got two different graphs here. One is a graph with the different accelerating potentials, and another one is a graph with the same accelerating potential but with the different target materials. Just we can discuss one by one. When you observe a graph or when you observe a plot, you will be getting two different curves. One is a continuous X-ray spectra and another one is a characteristic X-ray spectra. A continuous curve is obtained with all possible wavelengths. You can see a continuous spectra is obtained with all possible wavelengths with certain minimum wavelength. As the accelerating potential increases, the minimum wavelength decreases. See this one? As the accelerating potential increases, the minimum wavelength is moving towards the origin or moving towards the left, which explains that the minimum wavelength and accelerating potential varies inversely. So, when a fast moving electron strikes the target material of higher atomic weight, The electron loses its kinetic energy. The kinetic energy which is lost is given out in the form of X radiations. That's what we are speaking about. The X radiations will be giving out means electrons will be giving out their kinetic energies in different proportions. They will not be giving out all the kinetic energies to the target itself. Part of the energy may be given by the electron, or whole of the energy may be given by the electron. So we will be getting different values of wavelengths of X radiations, and the different wavelengths of X radiations are marked as a plot. So we will be getting a continuous range of wavelengths or frequencies with certain minimum value of wavelength. When we speak about wavelength, you have to speak about wavelength alone. So we will be getting a wide range of wavelengths of X radiations with certain minimum wavelength. This kind of curve obtained is called a continuous X-ray spectra. If you just look at this particular graph, on this continuous X-ray spectra, you are getting some lines with narrow peaks which are corresponding to certain well-defined wavelengths. And these peaks corresponds to the material of the target, means it depends upon the characteristics of the material of the target. Henceforth we call these spectral lines or these line spectra or otherwise these narrow peaks as the characteristic X-ray spectra. So these characteristic X-ray spectral lines are superposed over the continuous X-ray spectra. This is how we have to speak out. So the characteristic X-ray spectra are superposed over the continuous X-ray spectra. The characteristic X-ray spectra depends upon the accelerating potential between the electrodes. The continuous X-ray spectra depends upon the accelerating potential between the electrodes. The characteristic X-ray spectra depends upon the target material used, because it depends upon the characteristics of the target material. What is the meaning for the characteristics of the target material here? Why do we call so? Why we are speaking about the characteristics of a target material? You might have studied in the structure of atoms. When you are having discussion about Bohr atom model, there you might have seen the emission of spectral radiations is due to the transition of the electrons from higher energy levels to lower energy levels. If an electron jumps from higher energy level to lower energy level, if the energy gap is less, the emitted radiation will have more wavelength. If the energy gap is more, the emitted radiation will have less wavelength, because energy and wavelength are inversely proportional. Or otherwise, in terms of frequencies, I can say if the energy gap is less, the emitted radiation whose frequency is less. If the energy gap is more, the emitted radiation whose frequency will be more. So, depending upon the energy gap between the energy levels of an atom, the emitted spectral radiations whose frequencies and wavelengths are determined. So, we used to refer this particular narrow peaks on this X-ray spectra as the characteristics of the target material. Henceforth, this spectra is called the characteristic X-ray spectra. This is how we have to find the difference between continuous and characteristic X-ray spectra. From the spectra, two important features have been observed which cannot be explained on the basis of classical electromagnetic theory. Classical electromagnetic theory explains that when an electron is decelerated, then it gives out energy, it radiates energy. If it is the case, with the help of electromagnetic radiations or with the help of electromagnetic theory, we have to, or we could able to explain about two important features here. But with the help of electromagnetic theory, we cannot able to explain the features here. What are the features? One, we just observe this graph. For the same accelerating potential applied between the electrodes, here 35 kilovolt potential difference is applied between the filament and the tungsten target. The same 35 kilovolt potential is applied between the same filament but molybdenum target. Two different targets have been taken, but the potential difference applied between the filament and the target is the same. Now, when you draw the graph for these two different target materials, you could see that the two target materials have the same lower limit of wavelength. See this one? So same lower limit of wavelength. We used to call it cutoff wavelength. We used to call it cutoff wavelength. Both the targets have the same lower limit or the same cutoff wavelength. This has not been explained by this classical electromagnetic theory. First one. Second thing is that, second feature is that, if you observe the curve, for tungsten there is nothing. For molybdenum, you are getting two peaks. We call it K alpha and K beta lines. K alpha and K beta lines. So if you just look at this spectral lines for molybdenum, you can see narrow peaks superimposed over the continuous spectra. This narrow peaks corresponds to well-defined wavelengths. What does this meaning, well-defined wavelengths? If you mark a line from the peak, you will be getting a single value wavelength. We used to call it well-defined wavelengths. It will not possess range of wavelengths. It will possess a definite wavelength. So for K alpha line, you will be getting a definite wavelength. Or let me call this as lambda alpha. And then for K beta line, you will be getting a definite wavelength. Let me call this as lambda beta. What is the cause or what is the reason for the origin of these two narrow peaks on the continuous X-ray spectral radiation? This was also not been explained by the classical electromagnetic theory. But these two features, the existence of the same lower limit of wavelength for different targets and the existence of peaks over the continuous spectra, can be explained, or this could be explained on the basis of photon theory of radiation. We are going to discuss about that one by one. We shall now start with this continuous X-ray spectral radiations. We shall speak about the origin of continuous X-ray spectral radiations. As we saw, when a fast-moving electron strikes the target of higher atomic weight, then X-ray radiations are produced. This is what we saw. So what happens there exactly? We can just have a closer look on this. Let us consider an atom of higher atomic weight. So electrons will be there. Let me mark this electrons. I am not marking the electrons on the outer orbit. This is enough to explain. When an electron happens to bombard the target, as we know earlier, X-ray radiations are produced when fast-moving electrons are suddenly stopped by the target of higher atomic weight. Now, an electron is bombarding the target material. As it approaches the atom, or as it enters into the atom, it will be approaching towards the nucleus actually. If the electron is approaching towards the nucleus, let us consider like this. The electron is approaching towards the nucleus. What will happen? The nucleus will be changing the path of the electron. Why? Either the electron will get accelerated or decelerated. So this electron will not move in the straight line further, instead it will change the path. The path of the electron will be changed because of the acceleration or deceleration of the electron by the nucleus of the target atom. By the nucleus of the target atom. What will happen if the electron gets decelerated? What will happen to the energy possessed by the electron, fast moving electron? When we say an electron is moving faster, then it means that the electron possesses a greater magnitude of kinetic energy. When the fast moving electron is suddenly stopped or suddenly slowed down or decelerated, what will happen? The energy, kinetic energy possessed by the electron will be lost in the form of radiation. What radiation is that? X-radiation. An X-ray photon will be emitted. An X-ray photon will be emitted by the decelerated electron. So this kind of emission of X-ray photons or X-radiations due to the deceleration of electrons is called Bremsstrahlung. It's called Bremsstrahlung or breaking radiation. Simple. It is not breaking, it is breaking. Breaking radiation in the sense you are applying brake to the electron all in a sudden, so it is slowed down. Because of the slowing down or deceleration of electrons, so you will be getting a photon with certain amount of energy. It will be emitted out with certain amount of energy. We can say here, this is called Bremsstrahlung or breaking radiation. What is Bremsstrahlung or braking radiation? When a fast-moving electron is suddenly stopped by a nucleus of the atom of a target material, then the electron will be decelerated. This decelerated electron will be emitting radiations in the form of photons. We call it X-ray photon. This kind of emission of radiation is called Bremsstrahlung or braking radiation. And the energy, or I can call it kinetic energy, which is possessed by the electron, will be equal to the energy of the photon. So I can say the energy possessed by the emitted photon is equal to the kinetic energy lost by the electron. Kinetic energy lost by the electron. An electron cannot lose all its kinetic energy, or we cannot predict what happens exactly inside. The electron may lose part of its kinetic energy, or electron may be losing completely all its kinetic energy, or electron may give out its kinetic energy in a different proportion. Depending upon the kinetic energy lost by the electron, the energy of the photon will result. So I can say photons with different energies will be coming out of the target. All the photons, X-ray photons, will not possess the same energy. Each and every photon will possess its own energy. It all depends upon the loss in kinetic energy of the electron when it approaches towards the nucleus. So we can say the emitted photons may possess different magnitudes of energy. Hence, we will be getting a range of wavelengths or frequencies of the emitted X-ray photons, which results you in a continuous X-ray spectrum. This kind of emission of radiations results in a continuous X-ray spectrum. And we can say here, if the accelerated electron possesses a kinetic energy which is equal to EV, where V is the accelerating potential. As I told you, if this is the amount of energy possessed by the electron, EV is the energy possessed by the electron. I can call it the energy of the electron. EV is the energy possessed by the electron. If this total initial energy possessed by the electron is completely lost, it is losing all its energy. If the total energy possessed by the electron is completely lost, then it is completely given out in the form of X-ray photon with high energy, with high frequency, or with lowest wavelength. So we can say here a photon of frequency h nu naught, where this frequency is the maximum frequency among all the emitted photons. This is the maximum frequency of all the emitted photons. Why? Here we are saying that the electron which is approaching towards the nucleus is completely losing all its kinetic energy. If the total energy possessed by the electron is lost, then it will be given out in the form of X radiations with maximum energy. H nu naught refers to the energy of the photon, which is maximum. And the nu naught is the corresponding frequency, which is also maximum. As you know, frequency and wavelength are inversely proportional. I can say Hc divided by lambda naught, where lambda naught is the minimum value of wavelength. So we can say here the emitted or the bombarding electron possesses an energy which is equal to EV, where V is the accelerating potential. And if this energy is completely lost, if this kinetic energy is completely lost by the electron at the time of bombardment with the target, then a photon of energy h nu naught will be given out, where nu naught is the maximum frequency, h nu naught is the maximum energy, lambda naught is the minimum wavelength, because frequency and wavelength are inversely proportional. On comparing these expressions, I can say EV equals Hc divided by lambda naught. Lambda naught is equal to Hc divided by EV. As you know, H is the Planck's constant, which is 6.626 in 10 power minus 34 joule second. C is the velocity of light, which is 3 in 10 power 8 meter per second. E is the charge of the electron, which is 1.6 in 10 power minus 19 coulomb. Then, substituting all these constant values, you will get 12,400 divided by V angstrom. So lambda naught, the minimum value of wavelength or the lowest wavelength or cutoff wavelength is equal to 12,400 divided by V angstrom. This formula is called Duan-Hunt formula or Duan-Hunt rule. Duan-Hunt formula or Duan-Hunt rule. This is lambda naught equals 12,400 divided by V angstrom. On looking at this expression, we can easily see that the minimum wavelength or the cutoff wavelength depends only upon the accelerating potential applied between the electrodes. Accelerating potential applied between the electrodes, which explains that whatever may be the target that is chosen in the discharge tube for the production of X radiations doesn't matter. Only the accelerating potential matters, which decides the minimum wavelength of X radiations. Minimum wavelength of X radiations. Thus, the production of continuous X-ray spectra and the origin of the lowest wavelength or the cutoff wavelength in the continuous X-ray spectra has been clearly explained on the basis of photon theory of radiation, which is in good agreement with the experimental results. Thus, we can say the minimum wavelength of X radiations purely depend upon the accelerating potential, whatever may be the target. So, in this graph, we can see this voltage is the cutoff voltage. Cutoff voltage. See, one is molybdenum, another one is tungsten. Whatever may be the target. If the accelerating potential is 35 kilovolt, then the minimum wavelength will be giving you this, minimum wavelength will be obtained as the same. So lambda naught equals 12,400 divided by V angstrom. What decides the value of lambda naught? The accelerating potential. So we can conclude that continuous X radiations or continuous X-ray spectra arises due to the acceleration or deceleration of electrons by the nucleus of the target atoms. And we can say, as the decelerating electron giving out or when losing its kinetic energy gives out this lost in kinetic energy in the form of X-ray photons. So this kind of radiation emission which is taking place from the deceleration of electron is called Bremsstrahlung or breaking radiation. And we can say the kinetic energy or the energy of the photon given out from the target depends upon the kinetic energy of the electron bombarding the target. If EV naught, we can say here, whatever the kinetic energy possessed by the electron may be, we cannot say the electron is losing all its kinetic energy. Either it may lose part of its energy, or it can lose the whole of its kinetic energy, or any proportion in which the kinetic energy may be lost. So depending upon that, the emitted X radiation will possess its own energy. So you will be getting a wide range of wavelengths or frequencies, which results in a continuous spectrum. This wide emission of different values of wavelengths or frequencies of X radiations result in continuous spectrum. One. And second thing is that if you are speaking about the minimum wavelength or cutoff wavelength of this continuous X-ray spectra, it can be explained very clearly. If an electron collides with the target atom, loses all its kinetic energy due to the deceleration of the electron, then the complete lost in kinetic energy will be given out in the form of X radiations of high energy. X radiations of high energy or lowest wavelength. We used to call it cutoff wavelength. The expression has been given. EV equals h nu naught, which is equal to hc divided by lambda naught. Or lambda naught is equal to hc divided by EV, which is equal to 12,400 divided by V angstrom. And this relation, lambda naught equals 12,400 by V angstrom, is called Duan-Hunt formula or Duan-Hunt rule. Right? Thus we can say the minimum wavelength of X radiations from the expression depends upon the voltage or accelerating potential applied between the filament and the anode. Thus, with the help of this photon theory of radiation, we can easily explain about the production of continuous X radiations as well as the origin of the lowest wavelength or the cutoff wavelength. We shall now discuss about the characteristic X-ray spectra, origin of characteristic X-ray spectra. If you look at the spectra, then in the continuous X-ray spectra, some narrow peaks are superposed over the continuous X-ray spectra for certain well-defined wavelengths. We discussed it earlier. For certain well-defined wavelengths, I told you well-defined here refers to a single value of wavelength, single value. We call it single value. For single valued wavelength, you will be getting narrow peaks like this. The narrow peaks which are superimposed over the continuous spectra is due to the emission of radiation when a target is bombarded by the electrons with high velocities. When fastest electrons hit the target with high energies, then we can expect this kind of narrow peaks. The line spectra, which is superimposed over the continuous spectra, is called characteristic X-ray spectra. This line spectra corresponding to these narrow peaks, which are superimposed over the continuous spectra, is called characteristic X-ray spectra. See the statement? So, we can conclude that when a fast-moving electron hits the target of higher atomic weight, as we saw, X-radiations are produced. And if the X-radiations emitted possess a narrow peaks which corresponds to well-defined wavelengths, then such spectra is called characteristic X-ray spectra, and this characteristic X-ray spectra is due to the electron transition in the target atoms. Electron transition in the target atoms. So what exactly happens is quite different from the explanation what we studied in continuous X-ray spectra. In a characteristic X-ray spectra, or the origin of characteristic X-ray spectra is due to the electron transition in the target atoms. We shall now speak about that. If you consider the energy level diagrams of the target atom, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. We call it the principal quantum numbers, which corresponds to K shell, L shell, M shell, N shell, O shell, etc. Right? Now, if the electron is bombarding the target with high energy, then the electron may happen to collide with the electron in the K shell. I can show it with the diagram here. If this is the octet structure, this is the atom, and this is the nucleus surrounded by electrons. This is the K orbit, L, M. Then we can say if the bombarding electron hits the electron in the orbit, if the bombarding electron or accelerated electron is hitting the electron in the innermost orbit of the target atom, this electron will be removed out. I can say this electron comes out of the K shell, creating a vacancy in the K shell. This bombarding electron may escape out or just move in the space between the orbits, or it will be coming out, emerging out. But on its way, it has removed an electron from the K shell, creating a vacancy in the K shell. Now, this vacant state or this vacancy will be filled by the electrons in the higher energy levels, like the electrons in the L, M, N, O orbits. If an electron from the L shell jumps to K shell, filling the vacancy in the K shell, then it results you a K alpha line. If the electron from the M shell jumps to the K shell and fills the vacancy, then it will be generating a K beta line. If it is from N to K, it is K gamma. If it is from O to K, it is K delta. In this way, we can just go on, K epsilon and so on. So you will be getting a series of spectral lines from the target atom. We used to call it the characteristic X-ray spectra. Earlier I explained, if the energy difference between the L shell and the K shell is less, then the emitted photon whose frequency is less, wavelength will be more. See the statement. I can explain it with the graph also. If you are considering this graph, if you just look at the graph here, the same target, tungsten target is there, which is bombarded by the electron, which is accelerated with different potentials, 20, 30, 40, 50 kilovolt potentials. If the potential increases, the energy of the electron, EV, also increases. Energy of the electron, EV, also increases. If the energy possessed by the electron is completely lost, just look at the idea, it is very clear. If the energy possessed by the electron is completely lost, then it will be given out in the form of X radiation with the high energy. I told you, high energy. So high frequency photon will be emitted. Low wavelength photon will be emitted. If the potential is less, minimum wavelength or cutoff wavelength will be more. If the potential is more, then the cutoff wavelength will be less. This is what is observed from the expression. And then the same can be explained here with this transition also. If you just look at the transition here, the energy difference, as you know very well, E equals h nu, or I can say here, the transition is taking place between EL to EK. This will be giving out a photon of energy, let us say h nu. A photon of energy h nu, or a photon with wavelength hc divided by lambda. If this happens, then you will be getting a spectral line here. If the electron jumps from L shell to K shell, I will be getting the spectral line corresponding to this particular transition, which we call it K alpha line. As the electron reaches the K shell, we call it a K line. So it is K alpha line. If the jump is taking place from M shell to K shell, any of the electron from any of the outermost can jump to the vacancy. All the electrons will not come and fill the vacancy. Don't mess up your idea. If this vacancy is created, either an electron in the L shell will be jumping into the K shell, or from the M shell will be jumping into the K shell, filling up the vacancy, creating this K series of lines. If the same happens in the case of L orbit, if the bombarding electron removes the electron in the L orbit, what will happen? A vacancy will be created in the L orbit, and this electron or this vacancy will be filled by the electrons in the higher energy states. And you cannot expect an electron from K shell to jump into the L shell. You must provide energy from outside. That won't happen. The vacancy in the L shell will be filled by the electron jump from M shell or N shell or from O shell. So long wavelength X radiations will be obtained. See the statement? Long wavelength X radiations will be obtained. Why? When you compare the energy difference between K shell and L shell, the energy difference between L and M, L and N, and L and O differs. It will be lesser in magnitude. If the energy difference is less, then the wavelength will be more. That's what I am telling you here. A long wavelength L series will be obtained. If you just look at the case, the vacancy in the L shell can be filled by electron from the M shell, or an electron jump from N shell to L shell, or an electron jump from O shell to L shell, which will be resulting in L alpha, L beta, L gamma line. If a vacancy is created in M series or M shell, then electron jump from N to M or O to M will take place. We used to call it M alpha, M beta, and so on. In this way, we will be getting the series of spectral lines corresponding to the characteristic X-ray spectra. If you consider a target molybdenum, for example, I had shown you here. In a molybdenum target, we are getting the narrow peaks K alpha and K beta. You just look at the diagram here. Why shall not we write K alpha and K beta? K alpha line corresponds to a low energy difference transition. Low frequency will be there for the K alpha line. High wavelength will be there for the K alpha line. So K alpha line is given a higher wavelength. As you go from 0, K alpha line is given a higher wavelength, and K beta line is due to the jump which is taking place from M shell to K shell, which is said to have a greater energy difference. When compared to this energy difference is greater. So the frequency of the emitted photon will have a greater magnitude, hence a lesser wavelength. So K beta line will have a lesser wavelength. Which one will have a greater wavelength, K alpha or K beta? K alpha will have a greater wavelength. See, three terms are discussed here: energy, frequency, wavelength. Here, energy difference is less for K alpha line. So, frequency is less, wavelength is more. Energy, frequency, wavelength. Energy and frequency are directly proportional. Wavelength and energy, wavelength and frequency are inversely proportional. As the energy difference is less, frequency is less, wavelength is more for K alpha line. Wavelength is less for K beta line. Wavelength is further less for K gamma line. You can just write in the increasing or decreasing order of wavelengths, even in frequencies. This kind of questions will be asked in examinations. So, if I speak about the increasing order of wavelengths, I can write K delta. In this series I am writing K delta or increasing order is taken. So, K delta is less than K gamma, less than K beta, less than K alpha. Means K alpha is greater than K beta is greater than K gamma is greater than K delta. So K alpha has a greater value of wavelength, K delta has a lesser wavelength, lesser value of wavelength in this K series. So you will be getting series of lines which are superimposed over the continuous spectrum. It is due to characteristic X-ray spectra is due to the electron transitions that is taking place in the electron transition which is taking place in the target atom. So this is how the characteristic X-ray spectra has been obtained. When bombarding electron hits the target, it happens to hit the electron in the K shell so that the electron will be removed out of the K shell. A vacancy will be created. Vacancy will be filled by the electrons from the outer orbits. So this electron transition results you in the emission of radiations which corresponds to X-ray photons. The wavelength and frequency of the emitted radiation corresponds to the X-ray range of frequencies and wavelengths. That's why we are getting a characteristic X-ray spectra due to the atomic transition or electron transition in the target atom. So a continuous X-ray spectra is due to the deceleration of electrons when the fast-moving electrons happens to pass through the target atoms. And the characteristic X-ray spectra is due to the electron transitions in the target atoms. The electron transition that is taking place in the target atoms. I think the idea will be clear for you people when you have a comparative study between continuous and characteristic X-ray spectra. We shall now speak about the applications of X-rays here. Applications of X-radiations. X-radiations are vastly used in many fields. We shall now list out some of the applications here. One is medical diagnosis. X-radiations can easily penetrate through flesh, but it cannot penetrate through bones. Bones will stop the X-radiations or absorb the X-radiations, whereas flesh cannot. So, when you take an X-ray radiograph, a deep shadow of bones and a light shadow of muscles will be obtained on the radiograph. With that, we can go on with the diagnosis. So with the X-ray radiograph, you can easily find out the fracture in bones, you can find out the foreign bodies in our body, and also you can find out the diseased organs. That's why when you visit a doctor, in order to diagnose what is wrong with you, they'll ask you to take a CT scan. CT here refers to computerized tomography. CT scan will be taken with the help of X radiations to diagnose our body. So medical diagnosis is done on the basis of taking these X-ray radiographs. So deep shadow of bones will be obtained. You might have seen all the X-ray photographs over here, radiographs over here, where deep shadow of bones will be seen when compared to the shadow of muscles, which is very light. So you can easily detect the fractures in your bones. You can detect the foreign bodies. When a child happens to swallow a coin, that can be easily be seen with the help of an X-ray. And also you can study about the diseased organs. So you can diagnose. Second thing, you have to speak about medical therapy. Medical therapy. As X-radiations are capable of killing the diseased tissues. They can kill the diseased tissues. So, X-radiations can be used to treat or used to cure skin diseases and also to cure malignant tumors. If any tumor is there on in your body, then with the help of X-radiations you can remove the malignant tumors. Also, you can use the X-radiation to treat skin diseases. So, medical therapy is done with the help of X-radiations. And the third one, industry, industrial applications. Industrial applications. In industries, it is used to detect the flaws. It is used to detect the flaws in welded joints. Let us say an aeroplane body is constructed. Then if one metal is welded along with another metal, you should not lose any minute hole in the welded joint. If it is there, then during its journey, it will happen to catch out with fire. So you have to weld it very carefully. So with the help of X-radiations, it is used to detect even minute flaws in welded joints, tennis balls, and also in wood. All this can be identified or studied with the help of X-radiations, and it can be cleared out. And also in custom posts, these X-radiations are used to check out the contraband goods. Contraband goods are the restricted goods which a passenger should not take from the foreign countries. So if they happen to take a gold or jewelry or any cocaine sort of thing with their luggages, then they can be easily found with the help of these X-radiations. So X-ray scanners are used in custom points to check out the contraband goods. So in industries, they are used to detect the flaws in welded joints, even in metals, and also wood, even in tennis balls, in making tennis balls. In all these places, you can use these X-radiations. Also in custom points, these X-radiations are used to study or to check out the contraband goods. Then finally, scientific research. Scientific research. X-ray diffraction study is an important tool in the study of crystalline structures. X-ray diffraction studies. We call it X-ray diffraction studies. It is an important tool in studying about the structure of crystals. X-ray diffraction studies is used to study crystal structures. Crystal in short is written as XTAL, crystal structures. Crystal structures. That is, you can study the structure of atoms and molecules in a crystal in detail. So, in X-ray crystallography, we used to call it X-ray crystallography. In X-ray crystallography, the main purpose of the usage of X-radiation is to study the structure of crystals, how the atoms are arranged in a crystal, how the molecules are arranged in a crystal. So X-rays are used as an important tool in the X-ray diffraction studies. This is about the scientific research. So in medical diagnosis, in medical therapy, and in industry, also in scientific research, X-radiations are used. We shall now see a simple problem. Example 7.9. You are asked to calculate the cutoff wavelength, lambda naught, and corresponding cutoff frequency for an accelerating potential 20 kilovolt, which we write 20,000 volt. 20,000 volt. From Duan-Hunt's formula, we can calculate lambda naught, which is the cutoff wavelength. Lambda naught equals 12,400 divided by V angstrom, which is 12,400 divided by accelerating potential is 20,000. 20,000. This is angstrom. You can cancel these values. 124 divided by 200. I can write this as 62 divided by 100 angstrom, which is 0.62 angstrom. This is the cutoff wavelength 0.62 angstrom. And also you are asked to calculate cutoff frequency. Cutoff frequency is nu naught is equal to C divided by lambda naught. So 3 into 10 power 8 divided by 0.62 angstrom, which is 10 power minus 10. So this will be 10 power 18. So 3 divided by 0.62. 3 divided by 0.62, which will be 4.84 into 10 power 18 hertz. This is the cutoff frequency. So for accelerating potential 20,000 volt, the cutoff wavelength is 0.62 angstrom, and the cutoff frequency is 4.84 in 10 power 18 hertz for the given target metal.